in the plenary, we were thinking of something useful, a topic that would be of the interest of the IETF crowd. And I mean, regarding 5G, that we are basically, as I mentioned, getting a lot of requirements. There's going to be a lot of work actually in the IETF going on in the next 12 months. We thought that, cellular security would be good. But not only basically talking about what we're doing regarding 5G, but also a bit of historical background, of how security was in previous cellular systems. So as usual, we try to organize these things with IETFers, and John is actually involved in the security groups here. So we thought it was a basically good arrangement. So John, please.
Yeah, thank you, Gonzalo, for that nice introduction. So this will be about cellular security, and it will be about network security only, not about the application layer. If you think of Wi-Fi network, then you know what this is about. And it will be about 3GPP cellular systems only. It used to be a lot of competing standards, but now with LTE and 5G, it's 3GPP only. So this presentation will be basically in two parts. One historical part going through how the security in 3GPP cellular systems have evolved from the analog 1G systems to GSM to 3G and 4G. And the second part will be quite focused on concrete story of some of the things that the industry is driving in 5G. So starting from the beginning, and there's basically been one generation cellular system each 10 years. So the first 1G systems that were launched in around 1980. They were complete analog, and there was basically no security considerations when they were made. They were analog, so you could very easily eavesdrop on them, just using an ordinary radio that could turn in the right frequency. And basically the charging was that the phone sent its ID in clear text, and the network charged that to the right bill. So anybody eavesdropping on the ID and being able to reprogram the phone could call for free on someone else's bill. And development of the next 2G system started quite soon after in '82. And as a comparison, I have some non-3GPP things here. For example, here you have DES, was published in '77. So 2G, completely digital, but still circuit switched, not packet switched. For 2G, there was a large security focus, but still, the main goals was to fix the problems with 1G and make it as secure as a fixed phone. It was not intended as a military-grade secure communication. And it was probably the first mass-market communication system with cryptography in the world. Very widely deployed. And this was not appreciated by intelligence agency. Another fun thing, GSM is still up and running and will be for many years, but it was deployed expecting a 10 years lifespan. And GSM was standardized in '87, deployed in 1990. And you can see that was way, way before SSL, or for example, Wi-Fi with WEP, which was 10 years later and extremely less secure than GSM. This is how authentication in 2G GSM looks like. The phone and the network has a shared secret here called K, a symmetric key. The phone sends its identity called IMSI to the network, and this is sent in clear. And this is a problem. You can track this identity. GSM uses some temporary identity, but you can force the phone to reveal its long-term identity. The home network sends some random number and the authentication check and a key. The random number is sent to the phone. The phone calculates this authentication string, and this MSC node compares the values got from the phone and the values got from the home network to see if the phone is authenticated. Then the phone derives this key KC, and you have encryption between the phone and the base station. I will point out this was a very long time ago. Nobody really knew how to make secure authentication and negotiation protocols. So one thing is that the IMSI sent in clear text. Another is that the negotiation is not integrity protected, the algorithm negotiation. A third thing is that basically the key derivation does not include the cipher algorithm. And maybe the largest weakness is that it's only the client, the phone, that is authenticated. The network is not authenticated. And we will talk about how that was, most of these things have been fixed since then. GSM was designed in a completely different time. Cryptography was seen as, for a long time, seen as classified as weapons for export control. Now they are classified as dual use. There was also no clear definitions of what consisted strong cryptography, just that strong cryptography was not allowed to export. There was very different rules, for example, in the US and the European Union. This became much clearer in 1996 with the Wassenaar Agreement. But even here, around this time, it was basically 56 or even 40-bit keys were the norm. And this applies for example, DES and also for GSM. GSM uses the algorithms are designed for 64 bits, but they are shortened to 56. This was in the Western world. For exportation to third countries, development countries, the industry was forced to introduce a weak version of the cipher called A52 with limited security. And these algorithms were not publicly reviewed. This was not possible to use, way too slow. Mobile phones of this time needed something much faster. And to my knowledge, the reason to have them secret was that basically they were deployed. So anybody finding weaknesses on them would not have been positive. Next, we jump 10 years into and 3G. And basically here, a lot of the weaknesses in GSM was known. So the main goal in 3G security was to fix the weaknesses in GSM. One thing is mutual authentication with some replay protection. The signaling is integrity protected so that you cannot do a bidding down attack on the ciphers. The algorithms was public and were reviewed. AES is used for key derivation and authentication. Kazumi and SNO was used for encryption and integrity. This was previously published ciphers. Yeah. Security level is 128-bit everywhere. And the radio encryption was extended further into the network. And UMTS launched in 2001, around the same time as TLS 1.0, and the same year as AES and SHA-2 was. Then 5 years later, we got HSDPA, which was really the start of mobile broadband, raising the speeds enormously. And 3G is actually, to a large extent, still very secure. There's no serious attacks on 3G. Then 4G, also called LTE. And the goal here was to make it at least as secure as 3G, improving the security here and there. For non-security reasons, the encryption was moved out in the access network again into the base station, but also IPsec was added from the base station deep into the core network. And just as HTTPS now is used to a large degree on the web, IPsec is now really getting deployed into the PP networks. And I've seen figures expecting 80% use in a couple of years. LTE use AES for encryption and integrity, AES and SHA-256 for key derivation, and it's prepared for 256-bit keys, even if that is not used. And it's launched 2009, around the same time as TLS 1.3, 1.2, and the ciphers here are perfectly fine. Then we had, let's see, no. LTE Advanced was a higher speed version launched in 2013, and then 2014 VoLTE was launched. VoLTE is voice services over LTE, and LTE is packet switched only. The circuit switched options from earlier cellular releases were removed. Let's see how do I do with time. 4G, one of the main additions in 4G was the key hierarchy. And if you want, we do have time for short questions during the presentation also, but otherwise we take the main questions after. Basically, one of the main design goals for LTE was to never reuse the same key twice. So basically, you derive a new key depending on which algorithm you use, you derive a new key depending on which node it is, and when you do handovers between inside LTE or between LTE and other systems, you also do new key derivation. So basically, a lower down in the key does not allow an attacker to derive a higher key, and also keys at the same level does not allow you to derive some other key. And in the handovers, LTE provides both forward and backward secrecy, so that the new node cannot derive the keys from the previous session, and the previous new node cannot derive keys for the new session. And 4G and LTE was really the first global standard. 2G GSM was deployed in parts, mainly in Europe and parts of Asia, Africa, South America. 3G, the 3G PP3D system, UMTS, was mainly deployed in Europe, some deployments in the US, but it had competition. 4G initially had competition from WiMAX, but WiMAX did not fly, and 4G ended up as the first really global cellular standard. Here's an overview of all the different ciphering and integrity and key derivation algorithms in the 3GPP system. I think this might be the only overview I have ever seen, and I made it myself. But basically, red here means that they are not secure, basically because of key length. Earlier algorithms, these up here are key derivation algorithms. These are deployed on the SIM card. And GSM was really ahead of its time with hardware-based client authentication in 1990. So these algorithms are implemented on the SIM card in the phone and also in the home network in the HSS. Earlier version, done when there was strict export control, used 56 or 64-bit keys. That is, of course, not secure by today's standard. And the first version also had a weakness so that SIM cards could actually be cloned if you did query them. If you got your hands on them, and you could query them quite many times, but practically in a lab at least. 3D introduced the millinage key derivation that builds on AES. And here we have 128-bit keys, and both input and output. And this is still considered very well deployed and still considered secure. To have a backup algorithm, 3GPP and GSMA standardize the CHUAC, key derivation algorithm. This builds on Kitchak, which was also the basis for SHA-3, but here it's used with slightly different parameters than SHA-3. And that comes with a minimum length of 128, but also an option for 256-bit keys. Then there's quite a lot of algorithms for integrity and encryption. The oldest ones, let's see, A51, A52, they are built on LFSR to be able to run them on phones in the 1990s. And they use 64-bit keys, which make them insecure by today's standard. A51 is actually, there are some theoretical attacks on A51, but in practice, the best practical attack on A51 is still brute force, either by testing all the keys or lately by generating a rainbow table. So basically, A51 is actually giving you almost as good security as the key length. A52 is the export version that uses the 64-bit keys, but it does not offer 64-bit security, and it was never intended to do either. A53 is built on Kazumi. This is secure, but it uses a short key, so you can brute force it. And basically all these comp algorithms and the A5 algorithms, they were initially secret. They have later been reverse engineered and leaked. Kazumi is a block cipher that was the basis for the first ciphering in the 3D system. It's an evolution of this block cipher MISTY. It's used for both encryption and integrity protection. Later, SNO 3D was added. This is basically 3GPP and GSMA took SNO 2G, a very well-known stream cipher, and then it added some extra additions because there was some theoretical speculation that SNO could be susceptible to algebraic attacks. Later versions is AES. I would think that SNO 3D and AES is probably the most used today. 5G will likely reuse the ciphers from 4G as a start, might add more specialized, I don't know, faster or 256-bit versions later. So why do people still consider cellular networks to be insecure? I think if you read the media, there's quite a lot of negative attention. And I think and also here in IETF, I think cellular security has a very negative, people in general have a negative feeling. I think that is mainly because of 2G GSM. That is, 2G GSM is not secure. It was designed 30 years ago today. It was definitely best practice security when it was released, and it was designed for 10 years use. Unfortunately, it's still used, and it will, I think all the GSM systems in the USA have been closed down, but in Europe, they will use for at least 10 more years for IoT purposes. Unfortunately, your phones will happily connect to a GSM network. And as the network is not authenticated, it will happily connect to a false base station as well. And to my knowledge, there's no way to disable GSM in today's phones, either iOS or Android. I would like to see that, but right now I don't think you can do that. And another problem with GSM is IMSI catchers, which can track your identity and track where you are, see that you have been in 2 places at the same time. And this has been, it's known that it has been used in, for example, trash cans in cities with IMSI catchers, then selling you personalized advertisement. And in media, these terms, false base station, IMSI catcher, or Stingray is often mixed together. And Stingray can do both of these things. It's a product from a company. IMSI catcher tracks your identity, and the false base station you can connect to and make calls. False base stations is only possible in 2G. IMSI catchers is possible in all the generations. So what will happen in 5G? And this is still heavily debated and there is ongoing work, quite early work in 3GPP. I think the high-level 3GPP work happens in 3 stages. First, SA1 is doing requirements, that's mostly operators. Then SA2 and SA3. SA2 is doing the architecture, very high level, and SA3 is doing high-level security. And then CT1, the CT groups takes over and make stage 3 low-level detail specifications of everything. So one thing that 5G definitely needs to take care of is the enormous growth in mobile traffic. So LTE was launched, I don't know, but around 2010. Then the data traffic in the mobile networks was quite small, and voice was still a large part of the traffic back then. Data from mobiles was growing, and data from smartphones also, but all quite small. After that, voice is basically flat. Data from tablets and PCs has been increasing steadily, but data from smartphone has formally exploded and are expected to keep growing. We are here right now, and from here to 2022, the amount of data is expected to increase 10 times. And if you're wired network, that would cause problems as well, but you can always have more wires. On wireless, the spectrum is limited. 5G will take care of this with adding new frequencies, very high frequencies that can be used, and also with beam forming, where the radio is basically a very narrow beam that doesn't collide with any other beams, leading to less noise and better quality, increasing the overall capacity. I think, however, that there is other main drivers for 5G security. And that is mainly IoT is a main driver for 5G in general and for 5G security. We have sensors, the automotive industry. Sensors, basically, IoT sensors put requirements on low energy. They may have very small data amounts, but it should be very energy efficient. And it might sleep a large part of the day. This is a very strong contrast to broadband and media, where you have very, very high bit rates. And then you have the automotive industry, where maybe latency is the most important thing. You want latency in the a few millisecond latency from you send a request, you get a response. And you also get, normally in cellular networks, all messages are sent from a user equipment to a base station and to another user equipment. In the automotive industry, you might want to have car-to-car communication. Then we have factories. We might want to control robots, for example. You have infrastructure, electric grids, etc. And so it's quite a large amount of different use cases that the industry sees for 5G. It has very different requirements. One use case is to use 5G more in industry. For example, in a factory, where the factory might have its own 5G network, but not really clear how the responsibility would be between the factory industry owner and the mobile operator, and which frequencies this would be running. Another very strong trend in 5G is that everything will be virtualized. And this is something already happening for 4G networks. But 3GPP systems has not initially been designed to be virtualized. So maybe if you consider virtualization from the start, you might end up with slightly different choices and divisions. And also, many IoT systems require things to be very, very cheap. There's no, you don't want too much hardware cost or cost for manual deployment and configuration. This is a high-level picture of a 5G system. I will not talk much about this, but everything will be virtualized. You will have SDN, and then Also, a big plan for 5G is that 5G will have edge computing and be a much more open system where other parties can deploy and run applications inside the network, maybe in the base station to get extremely low latencies. For example, for factories or for automotive or rail. Yeah. So what are some of the concrete problems, security problems left to solve? One of these are IMSI catchers. And this has gotten quite a lot of media attention the last years. There was examples of someone putting a lot of IMSI catchers and or false base stations around places in the US, and also the same thing in Norway. Uncertain who did this. Yep. And this is one of the goals that we would like to solve in 5G. Another thing that is under consideration, and at least the goal of Ericsson, is to have more flexible identity management in 5G. The requirement group in 3GPP, SR1, has already decided that 5G shall support alternative credentials. That means something else than the USIM application that today are stored in the UICC, which is commonly known as the SIM card. But the requirement does not say really what these alternative credentials would be. But a good guess is that it will be asymmetric crypto, public keys, and certificates. We also want a lot lower cost complexity for massive IoT, and for factories and industries wanting to use 5G, we want a lot more flexibility so that the 5G system can integrate a lot easier with existing AAA servers in industries and factories. And to mitigate the problem with IMSI catchers, basically the problem is that the identity is sent in clear text, and when it's not, you can force the phone to reveal its identity. And the quite obvious solution to that is to encrypt the identity with a public key in the home network. And this is possible today. It would definitely not have been possible when GSM was standardized. Phones back then could not do public key crypto with any good latency. It would have taken way too much time. Then you would have maybe waited 10 seconds to connect your call. That would not have been good. The solution will likely look like something like this. Probably the home network will still have it will run Diffie-Hellman, but probably not the ephemeral Diffie-Hellman, probably a static ephemeral Diffie-Hellman to reduce latency and bandwidth. But then probably not a long-term static, some static key that you can exchange, replace. So the home network would have a private key, Y. The user equipment would have the public key of the home network, G to the power of Y. And then the phone would generate X, send G to the power of X to the home network, and then encrypt the identity IMSI with a key derived from the Diffie-Hellman secret. And today the IMSI contains the identity of the SIM card, but it does also contain the identity of the home network for routing purposes. So that would be needed to still send in clear. But then the only thing a third-party attacker would see is which home network this phone is connecting to, and not the identity of the phone itself. And this would basically mitigate IMSI catchers in 5G. Then you would still have problems if an attacker can force you to go down to 4G or 3G. Another thing that is under consideration and driven for 5G is which kind of protocol should be used for authentication. Today, when the phone connects to 3GPP access, 3GPP radio technology, then it uses what is now known as EPS AK. It's basically the 3GPP authentication and key agreement protocol sent in raw form without any packet layer. When the phone connects to a non-3GPP access but uses the SIM card to authenticate, then EAP AKA is used today. And this non-3GPP access could, for example, be a Wi-Fi network owned by the operator. So today, EAP is only used for non-3GPP access, and the only supported EAP algorithms are EAP AKA and EAP AKA prime, which is a slight modification. The plan for 5G, which Ericsson is driving, is to use the IETF standard EAP everywhere. So basically, you have the same when you connect to a 3GPP access or when you connect to a non-3GPP access. And you use EAP irrespectively if you authenticate with a SIM card or if you authenticate with certificates. And then 3GPP would need to support more than EAP AKA standard, which is specified for SIM cards only. And the alternatives up for discussion today is EAP TLS and EAP TTLS or PAP. EAP TLS is basically you use the TLS handshake, and then when you authenticate, you don't set up a record layer. EAP TTLS is that you set up TLS and then you authenticate over the encrypted TLS connection. And here is one place where IETF work is very likely. For example, EAP TLS is the specification is quite outdated. I think it uses TLS 1.0. TLS 1.3 is quite different. Yeah, and 3GPP definitely would like to use TLS 1.3 only. I will personally make sure that 3GPP mandates TLS 1.3 as soon as it's published. Everywhere where TLS is used in 3GPP. A third thing that is under consideration is perfect forward secrecy. Today, the keys for traffic protection, for encryption integrity protection of traffic, the application data in 3GPP networks are derived from the long-term keys, symmetric keys stored on the USIM and in the HSS. And of course, you also generate the random number, and then you derive keys from that. And this is secure as long as the symmetric keys, the secret keys are secret. If they leak, of course, you get problems. And according to rumors, that is exactly what happened a couple of years ago. The rumors are that several different intelligence agencies hacked SIM card manufacturers and got access to a large number of secret keys. This would allow them to passively eavesdrop on cellular radio. This is, of course, only rumors, but at least one SIM card manufacturer have acknowledged that they had a massive breach, even if they did not acknowledge that any keys were the attackers got access to secret keys. And how do we mitigate this from happening again? And the answer is similar to the encrypted IMSI. We do key exchange with Diffie-Hellman. Basically, you do Diffie-Hellman, ordinary Diffie-Hellman, you send G to X, G to the Y, and then you do this in combination with the current 3GPP AKA. And of course, this would probably be mixed together to save the number of round trips. It might even be that you have a static key on the server side. And then both parties derive their keys using the long-term secret and the Diffie-Hellman secret. And currently, 3GPP is looking at using elliptic curve Diffie-Hellman. That's the current best practice. But this would need to be replaced in maybe 5-10 years from now, when quantum computer starts to be a threat. And there's several good candidates for post-quantum secure Diffie-Hellman. One is lattice-based, which might be the first alternative, for example, TLS, DTLS, but there the keys are quite large. In wireless network, you really want to have small keys to save bits. And here, supersingular elliptic curve isogeny Diffie-Hellman is likely a better choice. Here the keys are much smaller, but on the other hand, the computational cost is much higher. But we'll see. And basically, if you want more high-level information on this, Ericsson has published 3 quite recent white papers. One on 5G security, giving a high-level, quite non-technical description on what the scenarios, what the problems, and the solutions are for 5G security. Ericsson also has a recent white paper on IoT security, summarizing a lot of the problems facing IoT security and privacy and how they can be handled. Third Ericsson white paper is the cellular networks for massive IoT, describing the new improvements that have been made to LTE to handle IoT. Basically, 3GPP has done 3 different work items during the last year, 2 different enhancements to LTE, specifically targeting IoT, and 1 work item targeting GSM, where GSM has been, or GPRS has been updated with new algorithms to be secure long-term, at least 10-15 years for IoT. Yeah. And that's it. Any questions?
You had a article on the pulled up that DC was littered with IMSI catchers. In that article, it says that IMSI catchers can catch text, sell, and install spyware. Is that just creative journalism, or is that?
IMSI catcher could only see your identity and track and see that you are it's the same term, SIM card that was at this place, at this location, and this place at this location. But the term IMSI catcher is often mixed up with false base station. A false base station would, your phone would believe it's valid to the base station, connect, and you would make your call to this false base station, and the base station would be able to eavesdrop on you. Of course, if you're using data traffic and your phone has some vulnerabilities, then the base station might hack you as well. But that might happen if you go to some web page and your phone has a problem as well. Yeah.
Hi. You didn't talk about the differences from 4G to 5G with respect to from base station to the S gateway, P gateway, or P gateway. Is there any changes there? Like earlier in 4G, we have SE gateway and all that stuff, right? So is there any, you didn't talk about that part actually. You're talking about always from EU to ENCRYPTED.
Yeah, there are some changes, but I don't know what the latest status on that is. On a high level, I think the security is more or less, the security solutions are more or less the same with some minor additions, but part of the architecture changes.
Hi, so you talked about the security improvements of the mobile handset to the base station covered in 5G, but as I understand it, the next generation of attacks are already happening on the SS7 and intra-base station communication, and do you have anything to say about what's in the store for protecting base station to base station or base station to network?
Yeah, SS7 is, I have not talked about application layer and not about the carrier net connecting different parts. I think SS7 is even older protocol than this. There's a large number of vulnerabilities. There's been several studies looking how you can fix these, but I think the answer is that you probably can't with backward compatibilities. I think you need to replace them, or and that takes time. But I think one of the main problems was that you could access the SS7 network online on the internet from some, in some places, and that of course made it very insecure. I think these problems have now mainly been fixed, making SS7 still has insecurities, but at least it's much harder to access them for a third party.
Henning Schultz-Henning, one question in terms of kind of a fake base station problem, that as you have roaming, international roaming in particular, how would a handset know which are good networks and which are bad networks? So I roam into country I visit, I have no idea what it's not none of my home network, and a rogue network happily will offer to serve me. And how would I know how would the device reasonably know which networks to support? Is there a mechanism intended that I can discover that? Right now, that doesn't seem to be the case. In the sense is, if I roam on 4G, if a network will let me on, my device will happily join it.
Yeah, but in 4G, if you use 4G or 3G, then the network is actually authenticated. So,
well, you know what it is, but I mean, when I roam to some country that I don't know, I have no idea if these network names are meaningless to me.
No.
And I can easily impersonate somebody who has not my best interest at heart.
Yeah, but if you do that in 3G or 4G, then you can trust that at least your home operator, which you hopefully trust, has trust this operator and allow your phone to connect to it.
So is there currently a mechanism, I just don't know, is there currently a mechanism in place that the home operator whitelists these networks? Because I don't know what, if my SIM card doesn't go, I don't have a channel to ask my home operator at that moment when I'm connecting. That's the whole point.
Basically, when you are connecting to this network that you don't know, then that network to be able, your phone to be able to connect to it, the roaming network has to talk to your home operator, and your home operator needs to allow your phone to connect to this network.
So it has to talk to your home network, because otherwise it won't get the keying material?
Otherwise, it cannot authenticate itself to your phone, and your phone would reject it. So that your phone connects to a 3G or 4G network, that means that this network has been authorized by your home operator. 2G, there is no operator, so then you don't know anything, yeah.
My name is Yang. Can you scroll up to the page use cases?
Which was that? This?
Okay.
Or?
Yeah.
Yeah.
So I see in 5G, the verticals probably very important use cases. So is there any special requirements in the security for this use case?
Which use case?
For example, in the transport.
Transport. Yeah, I think one of the main thing here is, one main requirement is latency, but that's not security related. What the security related come from that the bus needs, the cars needs to talk to other cars directly. So then you need to have a key exchange or key derivation in place, so that the cars can authenticate themselves to other cars and be sure that they're talking to who they're talking to, yeah, and that they get commands from the right. But today, all communication is user equipment base station, yeah, and you only authenticate that. So the main security thing here is that cars should be able to authenticate to each other when they are using 5G to communicate.
In this case, is there any new mechanism we need to introduce to get this kind of authentication?
Yeah, there's definitely new protocols and new key derivation, but hopefully they should work with irrespectively on what kind of credentials you use to authenticate to the network. So you authenticate, and then you would get keying material to authenticate to other cars. Yeah, but new protocols definitely needed. Yeah.
Hu Jun, from your presentation, you introduced there will be some changes between security design between the UE and the core network. So I'm wondering, is also going to be some change in the backhaul network between InnoB and the core network? So right now, and my understanding is that's 4G LTE using IPsec to increase traffic. Is there any change to that, or?
I think one of the large changes is that, which is already happening, is that everything is getting virtualized. So actually, before you had a radio encryption, and then you had optionally IPsec. When everything starts getting virtualized, you have the nodes divided from hardware. Even the base station will be run partly in hardware, out in the access network, and partly in the cloud. And then you would have maybe a TLS tunnel between these. So you will probably have several layers of security. You will probably have MACsec security, IPsec, and TLS, and maybe application layer security also.
Okay, thank you, John. There's like 3 minutes to the next session, so we have to wrap up. Thank you very much. I hope you guys found this interesting. If you have follow-up questions, please touch base directly with John. Thank you.
Okay. Yeah, sure.
And the next session is Opsay WG. So if you're interested in that, just stay here.
One of the things that I found very weird is the large number of messages that are actually received by the phone